Start by breaking down what a confidence interval actually is. Imagine you're trying to estimate the average height of all students in a school, but you can only measure a sample. A confidence interval gives you a range of values based on your sample that's likely to contain the true average height of all students. It's a way to express uncertainty in your estimate, showing not just a single number, but a range where the true value probably lies. This concept is fundamental in statistics because it helps us make informed decisions even when we can't measure everything directly. Confidence intervals are essential because they provide more information than a single estimate. Instead of just saying, the average height is 160 cm, you can say, we are fairly sure the average is between 158 and 162 cm. This range gives context and helps account for the natural variability in data. It's especially useful when making predictions or decisions based on incomplete information. By using confidence intervals, you acknowledge uncertainty and communicate results more honestly and transparently. Sampling is at the heart of confidence intervals. Since it's often impossible to measure an entire population, we take a sample and use it to make inferences. The sample mean is our best guess, but it's just one of many possible outcomes. Confidence intervals help us understand how much our sample mean might differ from the true population mean. The better our sampling method, the more reliable our confidence interval will be. This is why random and representative samples are so important in statistics. Confidence level is a key part of any confidence interval. It's usually expressed as a percentage, like 95%. This means that if you repeated your sampling process many times, about 95% of the calculated intervals would contain the true population value. The higher the confidence level, the wider the interval. It's a balance between being precise and being sure. Choosing the right confidence level depends on how much certainty you need for your conclusion. Interpreting a confidence interval correctly is crucial. If you have a 95% confidence interval from 158 to 162 cm, it doesn't mean there's a 95% chance the true mean is in that range. Instead, it means that if you repeated the experiment many times, 95% of those intervals would contain the true mean. This subtle difference is important for understanding what your results actually tell you and for communicating them accurately to others. Most commonly used confidence levels are 90%, 95%, and 99%. Each level reflects a different balance between precision and certainty. A 90% confidence interval is narrower, but you're less certain it contains the true value. A 99% interval is wider, but you're more confident. The choice depends on your field and how much risk you're willing to accept. For example, medical studies often use 95% or higher to minimize the chance of missing the true effect. Calculating a confidence interval involves a few steps. First, you find the sample mean and standard deviation. Then you choose your confidence level and use a statistical formula that includes a critical value from a table like the z-score for normal distributions. The result is a range around your sample mean. While the math can get technical, the basic idea is to create a range that's likely to include the true population value based on your data. Standard formula for a confidence interval is sample mean plus or minus the critical value times the standard error. The standard error measures how much your sample mean is expected to vary from the true mean. The critical value depends on your chosen confidence level. This formula is the backbone of confidence interval calculations and is used in many fields from science to business. Critical values are numbers from statistical tables that correspond to your chosen confidence level. For a 95% confidence interval, the critical value is typically 1.96 for a normal distribution. This value helps determine how wide your interval will be. The higher the confidence level, the larger the critical value and the wider the interval. Understanding critical values is key to correctly calculating and interpreting confidence intervals. Standard error is a measure of how much your sample mean is expected to vary from the true population mean. It's calculated by dividing the standard deviation by the square root of the sample size. The smaller the standard error, the more precise your estimate. In confidence intervals, the standard error helps determine the width of the interval. A larger sample size means a smaller standard error and a narrower confidence interval. Sample size plays a big role in confidence intervals. Larger samples provide more information and lead to narrower intervals, meaning your estimate is more precise. Small samples result in wider intervals, reflecting greater uncertainty. This is why researchers aim for larger sample sizes whenever possible. It's a simple way to improve the reliability of your estimates and make your confidence intervals more meaningful. Confidence intervals rely on certain assumptions. For example, the data should be randomly sampled and in many cases normally distributed. If these assumptions aren't met, the interval might not be accurate. It's important to check your data and understand the limitations of your analysis. Being aware of these assumptions helps you interpret your results more accurately and avoid common pitfalls. Visualizing confidence intervals can make them easier to understand. Often they're shown as error bars on a graph, with the sample mean in the center and the interval stretching out on either side. This visual representation helps you quickly see the range of likely values and compare different groups. It's a powerful way to communicate uncertainty and make your findings more accessible. Point estimate gives you a single value like the average height from your sample. A confidence interval, on the other hand, provides a range of plausible values for the true mean. While point estimates are simple, they don't show uncertainty. Confidence intervals add context and help you understand how reliable your estimate is. Using both together gives a fuller picture of your data. Medical research, confidence intervals are used to report the effectiveness of treatments. For example, a study might find that a new drug lowers blood pressure by 5 mmHg, with a 95% confidence interval of 3 to 7 mmHg. This means the researchers are fairly sure the true effect is somewhere in that range. It helps doctors and patients understand the possible outcomes and make better decisions. Businesses use confidence intervals to forecast sales, profits, and other key metrics. Instead of predicting a single number, they provide a range, like next quarter's sales will be between $1 million and $1.2 million. This approach helps managers plan for uncertainty and make more flexible strategies. Confidence intervals are a valuable tool for risk management and strategic planning. Pollsters use confidence intervals to report public opinion. For example, a poll might say that 52% of people support a candidate, with a margin of error of plus or minus 3%. This margin is based on a confidence interval, showing the range where the true support likely falls. It's a standard way to communicate uncertainty in survey results and helps the public interpret the findings. Confidence intervals are closely related to hypothesis testing. If a confidence interval for a difference between groups does not include 0, it suggests a statistically significant difference. This connection helps researchers draw conclusions about their data and decide whether to accept or reject hypotheses. Understanding both concepts is key to interpreting scientific results. There are common misconceptions about confidence intervals. One is thinking the interval contains the true value with a certain probability. In reality, the interval is fixed once calculated, and the probability refers to the method, not the specific interval. Another misconception is that wider intervals are always worse, but sometimes they reflect honest uncertainty. Understanding these points helps you use confidence intervals correctly. Confidence intervals are powerful, but they have limitations. They rely on assumptions about the data and sampling process. If these aren't met, the interval might not be accurate. Also, they don't account for all sources of error, like measurement mistakes or bias. Being aware of these limitations helps you interpret results with the right level of caution. There are situations where confidence intervals aren't appropriate. For example, if your data isn't randomly sampled or if the sample size is too small, the interval may be misleading. Also, for highly skewed data or non-numeric outcomes, other methods might be better. Knowing when not to use confidence intervals is just as important as knowing how to use them. Confidence intervals aren't just for means, they can also be used for proportions. For example, you might want to estimate the proportion of people who prefer a certain product. The calculation is similar but uses the sample proportion and a different formula for standard error. This approach is widely used in surveys and market research. You can also use confidence intervals to compare two groups. For example, you might want to know if there's a difference in test scores between two classes. The confidence interval for the difference tells you the range of plausible values for that difference. If the interval includes 0, there may be no real difference. If not, the difference is likely real. In some cases, you might be interested in ratios, like the relative risk in medical studies. Confidence intervals can be calculated for ratios too, using specialized formulas. This helps researchers understand not just the size of an effect, but also the uncertainty around it. Ratios are common in epidemiology and economics. In regression analysis, confidence intervals are used to show the uncertainty around estimated coefficients. For example, if you're predicting house prices, each coefficient has its own confidence interval. This helps you see which variables have a real effect and which might just be noise. It's a key part of interpreting regression results. Machine learning models often use confidence intervals to quantify uncertainty in predictions. For example, a model might predict a house price of $300,000 with a confidence interval from $280,000 to $320,000. This helps users understand the reliability of the model's predictions and make better decisions based on the results. Bootstrap methods are a modern way to calculate confidence intervals, especially when traditional assumptions don't hold. By resampling your data many times, you can build up a distribution of estimates and create an interval from that. This approach is flexible and powerful, making it popular in many fields. Bayesian statistics, credible intervals serve a similar purpose to confidence intervals, but have a different interpretation. A 95% credible interval means there's a 95% probability the true value is in the interval, given the data and prior beliefs. Understanding the difference between confidence and credible intervals is important for interpreting results from different statistical approaches. In reporting results, it's important to include confidence intervals alongside point estimates. This gives readers a sense of the uncertainty and reliability of your findings. Good reporting also explains how the interval was calculated and any assumptions made. Clear communication helps others interpret your results correctly. Many statistical software packages can calculate confidence intervals automatically. Programs like R, Python, and Excel have built-in functions for this purpose. Using software helps avoid calculation errors and makes it easier to analyze large datasets. Learning to use these tools is a valuable skill for anyone working with data. Academic papers often report confidence intervals to show the reliability of their findings. Journals may require authors to include them, especially in fields like medicine, psychology, and economics. This practice promotes transparency and helps readers judge the strength of the evidence. Confidence intervals are a standard part of scientific communication. Meta-analysis combines results from multiple studies, and confidence intervals play a key role. By pooling data, researchers can create more precise intervals for overall effects. This helps synthesize evidence and guide policy or practice. Confidence intervals make meta-analyses more informative and reliable. In manufacturing and quality control, confidence intervals help monitor processes and ensure products meet standards. For example, a factory might use intervals to check if the average weight of a product stays within acceptable limits. This helps catch problems early and maintain high quality. Environmental scientists use confidence intervals to estimate things like pollution levels or animal populations. These intervals help communicate the uncertainty in measurements and guide policy decisions. By showing the range of possible values, scientists can better inform the public and policymakers. Sports analysts use confidence intervals to evaluate player performance and predict outcomes. For example, a player's shooting percentage might be reported with a confidence interval to show how consistent their performance is. This helps teams make better decisions about strategy and player selection. Educators use confidence intervals to assess test scores and program effectiveness. For example, a school might report average test scores with a confidence interval to show the range of likely values. This helps administrators and policymakers understand the impact of educational interventions and allocate resources more effectively. Financial analysts use confidence intervals to estimate returns, risks, and other key metrics. For example, an investment might have an expected return with a confidence interval, helping investors understand the range of possible outcomes. This supports better risk management and investment decisions. Engineers use confidence intervals to assess measurements, tolerances, and system reliability. For example, when testing a new material, they might report its strength with a confidence interval. This helps ensure safety and performance standards are met and supports better design decisions. Psychologists use confidence intervals to report the effects of therapies, interventions, and experiments. For example, a study might show that a therapy reduces anxiety by a certain amount, with a confidence interval to show the range of possible effects. This helps practitioners and researchers judge the effectiveness of treatments. Agricultural researchers use confidence intervals to estimate crop yields, disease rates, and other important measures. For example, a study might estimate wheat yield with a confidence interval, helping farmers plan for the season. This supports better resource management and risk planning in agriculture. Marketers use confidence intervals to estimate campaign effectiveness and customer preferences. For example, a survey might show that 60% of customers prefer a new product, with a confidence interval to show the range of likely values. This helps companies make data-driven decisions and optimize their strategies. Public health officials use confidence intervals to estimate disease rates, vaccination coverage, and other key metrics. For example, an estimate of flu cases might be reported with a confidence interval, helping guide public health responses. This supports better planning and resource allocation during health crises. Tech companies use confidence intervals to assess product performance, user engagement, and system reliability. For example, a new app feature might be tested and user engagement rates reported with a confidence interval. This helps teams make data-driven improvements and prioritize development efforts. Confidence intervals aren't just for current estimates, they can also be used for future predictions. For example, weather forecasts often include a range of possible temperatures. This helps people plan for uncertainty and make better decisions based on the likely range of outcomes. Wrap up: confidence intervals are a fundamental tool in statistics for expressing uncertainty and making informed decisions. They provide a range of plausible values for unknown quantities, helping you understand the reliability of your estimates. Whether you're working in science, business, or everyday life, understanding confidence intervals can improve your analysis and communication. Remember to consider the assumptions, limitations, and context of your data when using confidence intervals.